Welcome, everybody, to our second lesson in Chapter 3, Part 2, Implicit Differentiation. This is a skill that you will use as the chapter goes on and in subsequent chapters. And if you continue to take more calculus courses at university, there's usually 3 or 4 that you can take. You're basically doing the first one this year. If you choose to take more, you will use this skill over and over again. Now, sometimes people find this a little hard to wrap their heads around. So if you need to pause at any point or go back, remember, since it's a video, you can go back and do a question again. If you're finding the way I'm explaining it isn't quite clicking with you, don't forget that there's also Khan Academy that is available to you. And they do a pretty good job of explaining things as well. And some other helpful websites that I have put up on our team as a PDF for you to see if you'd like some other explanation or some different examples. So when we look at a function such as y equals square root of x cubed plus 1 or y equals x sine x, these are functions that we can describe explicitly in terms of another variable. In other words, we can easily isolate y and write it in terms of x. So when we find the derivative, we're deriving y with respect to x. If we were to graph these, we would have a y-axis and an x-axis, and therefore the slopes would be change in y over change in x. Other functions, such as x squared plus y squared equals 25, or xy plus 3x equals 4, are defined implicitly by a relation between x and y, meaning x and y are interdependent on each other. We might still be able to isolate the y and rewrite it in terms of x, but the way these are written, what this means is as x changes, y changes, but also if we change y, x has to change as well. They are related to each other in an interdependent way. So, for example, if I have, see if my tablet will work for me today. If I have xy plus 3x equals 4, this one, we can isolate y. So this is an implicit function. It's not already written as y equals. There's a relationship between x and y where they depend on each other. However, we do have the ability to rewrite this in terms of y. So if I want to do that, I can move the 3x over to the other side. I can divide by x. And I can leave it like this, or I can write it as uh, 4 minus 3x times x to the negative 1, or I can write it as 4 over x minus 3, or I can write it as 4x to the negative 1 minus 3. So there are a bunch of ways I can write this. So that my y is isolated. Now, if I want to find the derivative, I can use any of these to find my derivative. I would choose to use this last one here. Okay, so if y is equal to 4x to the negative 1 minus 3, y prime would be negative 4x to the negative 2, or negative 4 over x squared. Again, I would get the same derivative no matter which version of y I chose, but I don't like using this one here because I don't like having that x on the bottom. I would choose to rewrite it as a negative exponent. And the reason I'm not choosing one of the first two is the first one I need quotient rule, and I would like to avoid that like the plague. I don't like to use it unless I have to. And the second one I would need product rule, and that would be fine. But this last one is easier. So I chose to use that last function there. So we were able to find our derivative no problem. We didn't have any issues with that. Now, if we look at this next function I've given you, x cubed y plus 3xy squared equals x squared y, isolating y isn't really possible. So it's sometimes we've got these functions where isolating y is either very difficult or not possible at all. And so if we want to find the derivative of that function, like we can still graph this function on Desmos and we can still draw tangent lines to this function. It's simply that we can't solve for y and we can't find our derivative in our usual way. So we need to use something called implicit differentiation. And what this is we're going to differentiate both sides with respect to x, meaning if I were to graph this, I would still have a y-axis, x-axis. And if I drew slopes of lines, I would have change in y over change in x, or the derivative of y with respect to x. And when we do that, you can choose to use y prime, or you're going to see this notation that I've mentioned before that is dy dx. And this is the same as y prime. So you've seen this notation here and there in your homework or in practice questions where it asks you to find dy dx. That's just y prime. So either notation is fine. I'm going to use dy dx because when we get to the next couple sections, that's the type of notation you're going to see. So reminder that if I have something like d dx of x equals 1, a reminder that what this means is this tells us find the derivative of x. So this means find the derivative of, and then for this question, we're finding the derivative of x, and we know that that derivative is equal to 1. The next one here says find the derivative of x squared, and that equals 2x. The last one, find the derivative of x cubed, and that equals 3x squared. Now, technically, what we have at the end of each of these is a little dx dx. We found the derivative of x with respect to x. This technically has a little dx dx, and this has a little dx dx. Now, the problem is dx dx, that equals 1, and that's why we don't see it here at all. Okay. If we want to find the derivative of y with respect to x, over here, this says find the derivative of. This bottom part tells us we are doing this with respect to x. Okay. So if I want to find the derivative of y with respect to x, the derivative of y is 1, but it is 1 dy dx. And so we almost can read this as this is 1 derivative of y with respect to x. Okay. So the dy dx indicates this is a derivative, but we took the derivative of y and not of x. Over here on this other side, because this is technically dx dx, that's why we don't write it. If we just have 1, this means I found the derivative of x with respect to x, and that gave me 1. The difference between these two is that if you're finding the derivative of a variable with respect to itself, we don't need to write this extra notation. What this tells me is this tells me I took the derivative of a different variable with respect to x. So the reason I can't just say this is because if all I knew was that it equaled 1, I wouldn't know what my original function was. I wouldn't know, was my original function x, y, w, t, m? We don't know. So if I did if I did d dx of t, this is going to be 1 dt dx. If I did d dx of m, this is going to be 1 dm dx. Those are really messy x's. Okay, so that dt dx, dm dx, dy dx tells the reader your original variable in your equation was a y or a t or an m. So it helps us figure out what was I dealing with when I started, okay? So let's make this a little neater now. Okay. So I'm going to go through a couple examples. I'm going to show you that whether you rearrange or do your implicit differentiation from the start, you'll get the same answer. But we're going to look at some questions where we cannot rearrange. Okay. This is one of those sections where the more questions you do, the easier it gets. The questions can get very messy, and often you can't actually simplify it very far. So just be aware if you are deriving a different variable with respect to x, you must include this. This is not optional. Okay, so let's try one. So this one, we can do this two ways. We can find the derivative now, or we can rearrange and then find the derivative. So I'm going to go back to some of our very basic notation, which you would not do each time. Okay. So if I want to find the derivative, this tells me I want to find d dx of x plus y, and I would need the derivative of both sides of this equation. On the left, we know that this can separate into two parts by adding the two derivatives together. Now, the derivative of x with respect to x is 1. Technically, it's 1 dx dx, but again, dx dx we don't need, plus 1 dy dx equals 0. Okay. So then if I move this one over to the other side, I get dy dx is equal to -1. Now, if I didn't want to show all of this writing, which I won't normally show, the derivative of x is 1. The derivative of y is 1 dy dx. And the derivative of 1 is 0. And then I can move the 1 to the other side, and I would be done. The last option is my very initial equation is x plus y equals 1. I can move the x to the other side, and then I can find my derivative, which would be y prime equals -1. Y prime and dy dx are just different notations. They mean the same thing. So y prime and dy dx are the same thing. So in your textbook, some of the examples, they might be using a y prime instead of a dy dx. That's fine. Okay? So notice no matter our method, rearranging, isolating y and finding the derivative, writing it as broken down as we can in the blue here, or doing the quick version in the black, we get -1 for all of these things. Okay. Now, the next question we're going to do, you'll see we cannot isolate y. There's no possible way we can. So if I want to find the derivative, I'm going to go term by term. My derivative of 3x squared is 6x. Technically, it's 6x dx dx. Again, we do not need the dx dx. The next one, we get 12y squared, and we need to include dy dx here because we took the derivative of y with respect to x. And the last one, the derivative would be 1 dy dx. Now, our job is to find dy dx. It said find the derivative. Dy dx is the derivative. So now our job would be to isolate dy dx. So we're going to move all the dy dx's to one side and get all of the terms with no dy dx's on the other side. So this is going to give us 12y squared dy dx plus 1 dy dx. So if I move the 12y squared term over to the right, and now what I can do is I can factor out that dy dx. And again, my job is to isolate dy dx. So my last step would be to divide both sides by 12y squared plus 1. We cannot simplify this at all. We're going to leave it like this. We are done. So this again is the same as saying y prime. So way back at the beginning of chapter 3, part 1, we did look at the different notations for derivative. And again, you've seen dy dx before. Now the difference is we're going to be using it more often instead of a y prime. But if you used a y prime here, that would work too. Okay. For the next one, the derivative on the left, cosine x plus y would be my derivative of sine. And then we need the derivative of the inside. So if I look at the inside, the derivative of x is 1. The derivative of y is dy dx. So we need chain rule for this. Okay. For the right-hand side, we're going to need product rule. Because the y squared and the cosine x are different functions, technically, that are being multiplied together. So the derivative of y squared would be 2y dy dx times cosine x, the original function, plus keeping the first function times the derivative of the second function. Okay. Now we're going to need to fix this up a little bit. Okay. On the left side, we need to distribute the 1 and the dy dx into our cosine. So we get 1 cosine x plus y plus cosine x plus y dy dx equals 2y cosine x dy dx minus y squared sine x. Okay. So just a reminder, this left-hand side here, cosine x plus y, you cannot distribute the cosine in here. That's not okay. You cannot do that. But the 1 plus dy dx that's separate here, where this part here, this is not inside the cosine. This is being multiplied by the cosine, and that's why we've essentially distributed the cosine into those brackets. Okay. So now we are at a point where we need to get all of the terms with no dy dx's to one side and all the terms with a dy dx to the other side. So I'm going to move my y squared sine x over to the left. I'm going to move my cos x plus y dy dx to the right. Okay. On the right, I can now factor out a dy dx. The left side would stay the same. And so my last step is going to be to divide by all the stuff that's on the right so that I can isolate my dy dx. Okay. So this question has a couple things involved here. We've got product rule, chain rule, and we have our implicit differentiation. So notice that really the derivatives you're finding aren't super difficult, but it looks really gross. There's a lot of rearranging to do. There's a lot of stuff we can't simplify. And so by the time we're done, I mean, that doesn't look great. There's nothing we can cancel. You cannot do this. Do not do that. Okay, that's not allowed. Okay, you can't simplify this at all. You're done. Okay. So your chain rule, product rule, etc., they all still apply. Nothing is different there. Okay. The difference is now you're going to have some y's, and anytime you find the derivative of the y, you're going to include a dy dx. Okay. So we're going to try one more. We're going to be finding the equation of an entire tangent line. Okay. So just a reminder, your equation of a tangent line is y equals mx plus b, where m is the derivative of your function. Okay. So we need to find the derivative of this function. So our derivative would be 2x is the derivative of x squared, plus 3y squared would be the derivative of y cubed. But again, we need to include dy dx. And then we're going to have minus 2 because 2 is our derivative of 2y. And then because we found the derivative of a y term, we're going to include dy dx. And then on the right side, the derivative of 3 is 0. Okay, so now we need to rearrange, isolate for dy dx. So I'm going to move the 2x over to the right for this one. I can factor out my dy dx on the left. And then I can divide by 3y squared minus 2. Okay. If you moved things to the opposite side, so if you moved all your dy dx's to the right instead of the left, you might have gotten 2 over 2 minus 3y squared. These are the same. The only difference between these two is the last version on the farthest right side, this one here, is if you take this one and you factor out a -1 on the top and the bottom and then cancel them out. So if you're finding you're checking your answers and all of your answers are like exactly backwards, meaning it's just all the signs are different, it just means you moved things to the other side of the equal sign, not that you're wrong. So if all of my negatives are positives for you and all of my positives are negative, your answer is correct. It's just a difference by a factor of -1 on the top and the bottom. Okay, so both of these would work. Okay, so now because we want to find the slope of the tangent line at the point 2, 1, we need to evaluate dy dx at 2, 1. And one notation you will see in the book is they'll write dy dx and then they'll put a line here and then they'll say x equals 2, y equals 1. And that means that that's where you're evaluating your derivative at. So if I do this, I'm going to get -2 over 3 times 1 squared minus 2, or just -2. Oh, whoops, I'm missing something. I forgot in my blue stuff, I moved 2x over. So if some of you were confused here, this is totally my bad. I moved this 2x over to the right and I forgot to write x. There should be an x on all of these. Which means I should have in the black, my derivative is -2 times 2 on the top, which gives me -4 over 1, or -4. So this is my slope at 2, 1. So go back and correct that if you didn't. These two and these top bits here, I had just 2. It should be 2x. Okay. Once you've corrected that, we have our m now. We want to find y equals mx plus b. We know that y is 1, m is -4, x is 2. So we're going to get 9 is b, and therefore y equals -4x plus 9. Okay. So again, if I'm finding the derivative of a term that has a y in it, the only difference is you're going to include that dy dx, change in y over change in x, or change in y with respect to x. Okay. And all the other derivative rules still apply. So if you have something like we had up here, where are we here? Like this guy, the y squared and the cosine x, That is a product of two separate functions. So you do need product rule there. Okay. That still applies. So if I have something like y cubed times x squared, we need product rule. Okay. We can't just leave the y alone. All right. So in the next section we are going to be using these to solve some word problems. Okay. And there's an extra practice sheet. If you go in the practice stuff folder and extra stuff, there's an extra practice sheet for implicit differentiation that has some really tricky ones in there. If you want to try, you can. And other than that, I would just say please make sure that you try some of these questions on your own, as sometimes people are okay to follow it when I do it. But when they start to try them on their own, they forget dy dx is here or there. So once you get the hang of it, it's not that bad. It's really a notation issue that people end up finding themselves in if they're missing things. It's usually because they forgot a dy dx somewhere. So go slow to start, try some practice questions, and if you have any questions or you're stuck on anything, please make sure you ask. Good luck.